Hi, this is Chemistry at Glance and my name is Aneta. So as the very last video for my AS level past papers is going to summarize all the acid-base titrations and the calculations that you need to be able to know for your exam. Okay, so let's just get into this. Francis measures the mass of hydrated copper sulfate, CuSO4 5H2O, and uses this to make exactly 250 centimeters cubed of copper sulfate. Solution of concentration 0.250 mol dm minus 3. Calculate the mass of hydrated copper sulfate required to prepare this solution. So, before you start, I just like to set everything out. So we have a copper sulfate solution. We're trying to find the mass of this. And then we have another solution. That's actually this. We have the same solution, but we're using this mass to make exactly 250 centimeters cubed of copper sulfate solution. And we also get the concentration. So whenever you got a concentration and a volume of one of the solutions, of any solution, you know straight away that you are going to have to find the number of moles. If we have a concentration and a volume, that always means you have to find the number of moles. So even if you don't understand the question at all whatsoever, just do this, because that will get you at least some of the marks. So we know the concentration, we multiply it by the volume, 250, but remember to change it to decimeters cubed, so times 10 to the minus 3, and that gives you 0.0625 mole. What we did is found the moles of the copper sulfate. We are asked to find the mass of this. So if we know the moles and we know the formula of this, we can use this equation and rearrange it to find mass, N times mR. However, you first need to find the mR of this solution. So let's do it right here. So the mR, copper is 63 point. Then we have sulfur, and this is 32.1. Then we add 16, but we times it by 4 because we have 4 oxygens. Then we add another 5 oxygens and 10 hydrogens. And all of this gives us 249.7. We have the MR, we have the number of moles, so we just gotta combine them. And the answer we get is 15.6 grams. So again, what we did, we found the number of moles of what we already knew. So that's the solution. So we measured a mass of copper sulfate and we made a solution of 250 centimeters cubed with this concentration. We found the number of moles. This is also the number of moles of the mass of the solid copper sulfate. We found the MR of copper sulfate. We used the moles and the MR to find the mass. Part B says, describe given full practical details how Francis should prepare the 250 centimeters cubed of copper sulfate solution. So preparing this solution is a preparing of a standard solution. A standard solution is the one for which we know the concentration, the one for which we're going to have the actual number of moles. So this is a very important one. So in preparation of a standard solution, we have one reactant, like this, copper 2 sulfate. We measure a mass. So we weigh the solid in a weighing bottle. Then we always add just enough water to dissolve the solid. We don't give a lot of water, just enough to dissolve it, so just a little bit. Then what you do, of course we have to remember to swirl in the solution. We have to remember to swirl the solution as well. After we dissolve it, we pour the whole solution to a volumetric flask. Volumetric flask is the one where we have a graduation mark, which will tell us when we reach 250 centimeters cubed. We use a funnel, and then after you pour it, remember to wash the weighing bottle and funnel. And what I mean by wash is that when you add water to 250 centimeters cubed, you can wash around the weighing bottle, swirl it again, and pour it through the volumetric through the funnel to the volumetric flask again, so that no product is lost whatsoever. And then you add water up to the graduation mark of 250 centimeters cubed, and that's the process. The next question says, Eleanor titrates a solution of potassium carbonate against a 0.2 molar HCl solution to find the concentration of the potassium carbonate. We're given an equation. Then it says she uses methyl orange as an indicator. This turns from yellow in the potassium carbonate solution to pink when the potassium carbonate is neutralized by the HCl. She obtained the following results using 25.0 centimeters cubed samples of the potassium carbonate solution. So here is our table with the final and initial readings on the burette. And now we're asked to calculate the mean titer that Eleanor should use in her calculations. If you don't know what I mean by final readings, initial readings of the burette or anything like this, go down to the description box below, click on the link to my blog and visit the blog post first when I explain each type of titration and what's going on in the titration. So just a summary, in the titration you have one reactant in the burette, one in the conical flask below, and then you let the reactant from the burette go to the conical flask until the end point. So before you start titrating, you read the value on the burette. When you finished pouring it in, when the end point is reached, you read it again. That's the final reading. And then titer is the difference. So that's the difference going to be what volume has been used to reach the end point. And that's what we're going to do right now. So 23.50 minus 0.40 is 23.10. That's going to be 23.95, 23.20, and 23.15. So that's our titers. And now mean titer is adding them all together and dividing it by the number of titrations, which is 4. However, before we do that, we need to remember that all titers need to be in 0.20 centimeters cubed distances. So looking at that table, that one and that one is 0.1 centimeters cubed difference. That one's 0.5 centimeters cubed difference, 0.5 centimeters cubed difference, but that one is way too high compared to these ones. So we're not going to include that one in our calculation. So we only do these 3. So that one and that one. And we divide it by 3, the number of titrations. And the answer we get is 23.15 centimeters cubed. B, describe the practical steps that Eleanor used to obtain a titration value. You should start by measuring 25.0 centimeters cubed of the potassium carbonate solution from a 250 centimeters cubed stock solution with the acid already in the burette. So we have our acid in the burette. So what we do at the beginning is measure 25 centimeters cubed of potassium carbonate, which is going to be our base. So the acid is already in the burette. So what you want to do, your first step is pipette 25.0 centimeters cubed of base to a conical flask. After you pipette it into conical flask, the solution from the burette, the acid from the burette, will drop to that conical flask. After we pipette it, we add some indicator to the conical flask. And indicator is needed there so that when we add the acid, we know when the end point is, because at the end point, the color of the indicator will change. And the next thing we gotta do is titrate with acid. Of course, we need to remember to swirl. Titrate with acid and swirl until the end point is reached. At the end point, the color of the indicator will change, so the color of the solution in conical flask will change, and you will see that this is the end of the solution. That's when the solution is going to be neutralized. So Eleanor's value was slightly lower than the actual value. When asked why, she stated, "I did not add the acid drop by drop at the end and so overshot the endpoint." State 2 other common sources of error in such experiments and explain why Eleanor's statement cannot be correct. Assume that all the equipment is clean and all the chemicals used are pure. Okay, so let's start with the error. So the other two errors could be wrong readings. So she could have read the on the burette. She could have read wrong in the burette. Another error that could occur is not swirling enough, or more than one person swirling, because everyone has a different way of swirling. One person can swirl it faster, the other one can swirl it slower, and then the amount added might differ slightly. We also asked to state why Eleanor's statement cannot be correct. So she said that she added the acid drop by drop. She didn't add the acid drop by drop at the end, so she overshot the endpoint. So if she overshot the endpoint, that means she added too much acid. And looking at our equation, if the volume increases, our number of moles increases too. So if the number of moles increases, that means the moles of carbonate would be bigger than the actual. So she was trying to find the concentration of the carbonate, but to find the concentration we would need the number of moles. So if she added too much acid, that means the number of moles would increase, and so the concentration would increase. However, her value was slightly lower than the actual value, and if she added too much acid, the value would actually be slightly bigger than the actual. So that's why her statement cannot be correct. She must have done something else wrong and not overshot the point. So, Rodri carried out the titration using a 2.0 molar hydrochloric acid solution instead of a 0.2 molar solution. State if he is likely to have got a more accurate result for the concentration of the potassium carbonate solution. Justify your answer. So, if he'd used that concentration is obviously bigger than this one. So, if we have bigger concentration, the volume needed would be smaller. If you have a smaller concentration, the volume needed would be bigger. But it's much easier to make a mistake when you have a small amount of volume compared to having a bigger amount of volume. So the answer is that the percentage error for smaller volume, so bigger concentration, 2.0 molar, is greater. Let's look at it this way. So if you have a big concentration, you just need a small amount of volume, and it's much easier to make a mistake when you need a small amount of volume than when you need a big amount of volume. Here's a big calculation question. So in an experiment to find the concentration of some dilute sulfuric acid, a student diluted exactly 10 times to give a concentration suitable for titration. He made up some standard sodium hydroxide solution by dissolving 1.00 grams of it in 250 centimeters cubed of solution. He then found that 25.0 centimeters cubed of the sodium hydroxide required 23.5 centimeters cubed of the diluted sulfuric acid for neutralization. Calculate the concentration of the original dilute sulfuric acid in mol dm minus 3. So as I told you before, whenever you have a volume of sodium hydroxide, wait a minute, we are kind of given the concentration of sodium hydroxide along with the volume. Volume is presented to us. He found that 25 centimeters cubed of sodium hydroxide. However, the concentration is said to be 1 gram of it in 250 centimeters cubed. So that's 1 gram in 250 times 10 to the minus 3 decimeters cubed. So 0.1 gram in 25 times 10 to the minus 3 decimeters cubed. So we had 250 centimeters cubed with 1 gram at the beginning, but we found that only 25 centimeters cubed of this sodium hydroxide is required. So if we divide it by 10 to get to 25, we have to divide. So we divided this side by 10 to get to 25 decimeters cubed times 10 to the minus 3 decimeters cubed. So we need to divide this side by 10 too to give us 0.1 grams. So if we know the mass is 0.1 grams, we can find the MR of sodium hydroxide, which is 40. We can find the number of moles, which will help us further along. You always want to find the number of moles because that's what you're always going to need. So we have the number of moles of sodium hydroxide. What we're trying to find is the concentration of original dilute sulfuric acid. So look back, what we know about the sulfuric acid. We know that the volume is 23.5 times 10 to the minus 3 decimeters cubed. So this much was required of the sulfuric acid. We have the equation, so we can work out the number of moles. 2 to 1, the ratio, it's 2 to 1. So to find the number of moles of H2SO4, we need to divide the number of moles of sodium hydroxide by 2. And this gives us, I know what I did wrong. That shouldn't be 1.25. That should be 2.5 times 10 to the minus 3. And when you divide it by 2, that's 1.25 times 10 to the minus 3 mole. That's right. So that was the number of moles we got from this reaction. When you divide it by 2 to get the number of moles of sulfuric acid, you get 1.25 times 10 to the minus 3 moles. So we have the number of moles of sulfuric acid. We have the volume of sulfuric acid. So now what we just do is moles over the volume to get a concentration of 0.0532 mole dm minus 3. However, let's not forget that the question is saying calculate the concentration of the original. And at the beginning, we were saying that some diluted sulfuric acid, a student diluted it exactly 10 times. So that concentration is 10 times diluted. So to get the original concentration, we need to multiply this concentration by 10. It was 10 times diluted, so now we need to multiply it by 10, which gives us 0.532 mole dm minus 3 as the final answer. Our very last example, past paper. This is an example of a back titration. So an indigestion tablet was crushed and an excess of hydrochloric acid, 25 centimeters cubed of 1 molar added. The resultant solution was titrated against the 0.5 molar sodium hydroxide, requiring 25.8 centimeters cubed of it. Calculate the mass of calcium carbonate in the tablet. Here are the two equations we have. So first of all, what we know. So let's focus on our first equation. So we know that resultant solution was titrated against this concentration and this volume of sodium hydroxide. So let's do N equals CV. 25.8 times 10 to the minus 3. Remember, it's the decimeters. And this gives us 0.0129 moles. What we also know is the number of moles of HCl, because we've been given it in the bracket. So it's 1 times 25 times 10 to the minus 3. That gives us 25 times 10 to the minus 3 moles. So that's the initial number of moles of hydrochloric acid. We then were left with 0.0129, because from this reaction, as you know, if that's 0.0129, then that's a 1-to-1 ratio. That has to be 0.0129. 0.0129. That's what here that we calculated. That's the initial number of moles of hydrochloric acid that were present. So that much were left after the first reaction of the crushed tablet. So what you want to do is 25 times 10 to the minus 3, and you take away the 0.0129, and you're left with 0.0121 moles. So that's what we had at the very, very beginning. That's what was left to react with sodium hydroxide. So this much must have reacted with tablet. If that much reacted with tablet, now we need the second equation. here, that's 0.0121 molar. That's what reacted with the tablet. That was the initial, that what we had reacting with sodium hydroxide at the end. So the difference is what reacted with the tablet. The ratio is 1 to 2. So we need to divide 0.0121 by, oh sorry, you can't see that, by 2 to get the number of moles of calcium carbonate, and that's 6.05 times 10 to the minus 3 moles. That's the number of moles of calcium carbonate. So our very last thing to do is to calculate the mass of calcium carbonate in a tablet. So our mass, we do N divided by D MR. Sorry, M is N times MR, not divided. So we know the number of moles. The MR we can calculate, which is 100.1, and we get this amount of grams. So this question might seem really confusing, but when you look at it, you were given what you had at the beginning. You were given what then reacted with sodium hydroxide. The difference must be what reacted with the tablet. Then you use the other equation with the tablet. This is a tablet, the calcium carbonate in the tablet, reacting with hydrochloric acid. We knew the number of moles of this hydrochloric acid. Because the ratio is 1 to 2, we had to divide the number of moles by 2 to get the number of moles of calcium carbonate. And after you got that, you just use our basic equation to find the mass. And you're done. So these were all the questions I had. Remember, everything I show you are my techniques and ways of learning and revising. If you have any questions about my videos, please comment or email me. I would like to hear something from you. I leave the links in the description box below, as always. Also, if you have any comments about the quality or content of my videos, please also leave them under this video. Thank you. And for now, like, subscribe, and see you soon. Bye!